For 50 years, making chips faster meant making transistors smaller. But around this decade, that quiet rule stopped being the hard part. The hard part moved outward, to how you stack the memory, wire dozens of chips together, and feed a starving processor fast enough. This is advanced packaging. And between 2026 and 2030, it is racing forward faster than at any point in its history. Three separate revolutions, memory, integration, and optics, are all hitting their turning points at once. Let's lay them on one timeline. Start with the problem. A modern AI chip can do enormous math, but math is useless if you cannot feed it data fast enough. The two things that feed it, memory bandwidth and chip-to-chip links, never kept pace with raw compute. Engineers call these the walls. There is a second limit. Chip-making tools can only print a pattern so big. No single chip can grow past that reticle boundary. So you break the design into smaller pieces called chiplets, then stitch them back together inside the package. Packaging becomes the real battlefield. Packaging now solves three things. Stack memory taller and faster, connect more chiplets on one carrier, and replace copper wires with light. 2026 is the year of validation. Everything ships in its first real form, and the industry proves the concepts work at volume. Memory first. This year brings HBM4 high-bandwidth memory, carrying the biggest architectural change in years, the base die split. At the bottom of every memory stack sits a control chip, the base die. With HBM4, it jumps to an advanced logic process. And that gets political. SK Hynix builds its base die on TSMC's 12-nanometer logic, so the memory leader now leans on the foundry giant. Samsung uniquely makes its base die on its own 4-nanometer process and packages in-house, the only true turnkey stack in the industry. Integration next. TSMC's CoWoS carrier holds the logic and memory on one silicon interposer, this year running about 5 times reticle size. Then optics. TSMC's silicon photonics platform, COUPE, enters production, stacking an electrical die on a photonic die to move data as light. One clever detail. NVIDIA and Broadcom keep the lasers off the package. Lasers hate heat, so light is piped in from front panel modules. Underneath it all, a quieter shift begins. Glass substrates. The old organic ones are running out of room. Glass stays flat and cuts signal power. Intel has already shown a package combining its bridge tech with a glass core. 2026 proves it out. Nobody ships it in volume yet. If 2026 is validation, 2027 is where the roadmap steps on the gas, across all three races at once. Memory moves to HBM4E. Data rates climb toward 10 gigabits per second per pin, and bandwidth pushes near 2.5 terabytes per stack. Integration takes a leap. TSMC qualifies a 9.5 times reticle package carrying 12 or more memory stacks beside leading-edge logic. And something wilder enters production. System-on-Wafer, which abandons the substrate entirely and builds a system across most of a whole wafer. Glass substrates cross toward mass production. If timelines hold, a flood of glass-based AI products begins arriving from every major vendor. 2028 is not another increment. It is where the industry finally retires a technology it leaned on for a decade. For years, memory layers were joined by microbumps, tiny solder balls. Now hybrid bonding fuses the dies directly. Copper to copper, no bumps. That enables HBM5, likely 20 layers tall, with the base die on a 2-nanometer process. NVIDIA expects it in late 2028. Integration hits 14 times reticle, one package carrying up to 20 stacked compute chiplets and 20 memory stacks as a single processor. And optics reaches the 3.2 terabit generation, the real inflection. Here copper cannot keep up, and light becomes the default inside the rack. By the decade's end, TSMC's roadmap points beyond 14 rickles, with as many as 24 memory stacks and nearly 50 times today's compute. This is the payoff. Hybrid bonded memory, a wafer-scale interposer, co-packaged optics, and a glass substrate. 4 revolutions arriving as one pack. Step back, and you see 3 different bets. TSMC bets on scale. Its packaging becomes the default carrier for nearly every AI chip on Earth. Samsung bets on turnkey, memory, logic, packaging, and soon optics, all under one roof. If the yields hold, no rival can match it. Intel bets on being the alternative. Its bridge packaging, glass substrates, and spare capacity aimed at the crunch its rivals created. Notice what they share. None of it is really about the transistor anymore. And every date here is a target. In this industry, targets slip. The direction is certain. The future of computing is being decided in the millimeters around the chip. Subscribe, and we'll keep decoding it.